Okay, so here's the video of me doing problems that will be similar to what you'll see on the exam, Unit 4 exam. So here's the format, and what I've written in red, you should write in before we get started. So let's number these problem types, because I'll be referring to them as, problem type 1, 2, 3, 4. So do those. When you get a chance, or maybe as we go, I've written down where in your packet you can find the problems that I'm going to do. But then also, I have added a seventh type of problem. And so you'll want to write this down. So given a function like this, where you don't have a, b, and c, but you are told that they are constants, use extrema, points of inflection, points on the original graph, critical numbers, etc., to set up a system of equations to find a, b, and c. And the problem that I'm going to do in probably the second part of this video is going to be from page 9 in this packet, number 92. But you could also find another example like this in the Unit 4 exam that I sent you or gave to some of you from last year, number 8. Okay, so the first thing I'm going to do is page 8, number 64, and this is going to cover, it's hard to see what that even is, but doing this problem will cover types 1 and 2. Okay, so types 1 and 2. You're given a graph of f prime or you're given a graph of f double prime, use Susan's table to make determinations about f. Alrighty, so this is number 64, and so you're given f prime, this is the f prime graph, this is the f double prime graph, and then we've got to do all of these things. So determine the critical numbers of f. Where is f increasing? Where is f decreasing? At what numbers, if any, does f have a local minimum? At what numbers, if any, does it have a local max? And then we've got things about concavity. Okay, well actually let me look. All right, so for these directions, I'm going to bracket off that because, actually let's look at this first. So these things you have to know by heart, guys. Susan's table and the physics version of Susan's table. For these problems here, I don't need the physics version. Okay, so Susan's table, so you'll have to know that by heart. And A through E, those are all having to do with f prime. And then F through H, this is where we'll need the F double prime graph. Okay, so first, determine the critical numbers of F. The critical numbers are where the first derivative is 0 or undefined. All right, so for part A, for number 64, I'm looking at F prime, and it is right here. So x equals 1. That is the only place where f prime is 0 or undefined. Okay, now for B, where is f increasing? So Susan's table says that f is increasing when f prime is positive. All right, so I'm looking for where f prime is positive. And you look at the f prime graph, it is positive from 1 to infinity, I guess. From 1 to infinity. And guys, I'm just using a bracket here because the answers in our book, I think, are using a bracket. But for the AP, I think the AP, I know I have seen sometimes just a parenthesis there, so I'm not going to be super picky about this until I can guarantee you which, whether the AP test graders will be looking for a bracket or a soft parenthesis, because maybe it doesn't matter. Maybe it could be either, I'm not sure. But I'll just do this for now because that's what the book will be saying. And on the test, I'll give you credit for either. Okay, so there's that. Oh, and also, make sure that you are able to do the following things: know Susan's table by heart and the physics version, and be able to use the information in these tables to write an explanation for your answers. So if they said, like, explain this, I would say, since f prime is positive on this interval, we know f is increasing, or something like that. Okay, so that's B. All right, C. Okay, where is f decreasing? F is decreasing when f prime is negative. F prime is negative. This is the f prime graph, so f prime is negative from negative infinity to 1. D. At what numbers, if any, does f have a local minimum? Okay, so for a minimum, we want a sign change. Alrighty. Okay, so this is going from, so f prime is going from negative to positive. Actually, let me go like this. All right, so this is an f prime number line. There's our critical number 1. Negative to the left, positive to the right. So if f prime changes from negative to positive, the original f changes from decreasing to increasing. So we've got a local min at x equals 1, no local maxes, because we would need f prime to change from positive to negative. Okay, so that's for D and E. D, no local max. Okay, so now F, G, and H, we're thinking about the F double prime graph here. Okay, so the F double prime graph. Where is F concave up? So F is concave up when F double prime is positive. Oh, you also could have used where F prime is increasing, because we have that graph as well. But it's where F double prime is positive, and then it'd be concave down where F double prime is negative. And then we'd have points of inflection where F double prime has a sign change. But as you can see, this F double prime graph is always above the x-axis. It's always positive, all right? And so E, okay, F concave up from, I guess, negative infinity to infinity. Okay, I think that this would be fine also. Negative infinity to 0. I think some books would say this, some books would say that. I would give you credit on the test for either one. Okay, and then, okay, E, F, G, never, okay, because F double prime is never negative. H, there are no points of inflection because F double prime never has a sign change. Okay, that was page 8, number 64. Let's do, okay, so now I have page 9, number 66. All right, let's do F through H only here, because the A through E are, you know, I don't feel like we need more practice with those. But the reason I chose to do another example that is covering this problem type is because you know, there were no points of inflection on the last one, so I just wanted to do an example where there were points of inflection. Okay, so F. All right, so F, where is F concave up? Concave up when F double prime is positive. All right, so F double prime positive is this interval and that interval. So this is negative radical 2 over 2. Negative radical 2 over 2 to 0. All right, and again, I feel like the book is using these brackets, if I'm remembering right. Radical 2 over 2 to infinity. Okay, and that's because F double prime is greater than 0. G, concave down. I'm looking for where F double prime is below the x-axis or less than 0. So it's going to be this interval and that interval. So negative infinity up to that, union zero. Okay? And then H, points of inflection at x equals this and x equals that, because F double prime has a sign change. Okay, so those examples we just did cover problem types 1 and 2. Now we'll move on to problem type 3. Given the function f, find f prime and use a number line test to find the relative extrema of f. So we'll do page 7, number 40, and actually we're going to cover problem types 3 and 4. Okay, so page 7, number 40 covers types 3 and 4. This is the function that they're giving us, and we're going to find local extrema, concave up, concave down, and point of inflection. Okay, so local extrema, that's where you're going to use f prime in a number line. Concave up, concave down, point of inflection, that's where we'll use f double prime in a number line. Okay, so for part A, you find f prime equals 6x squared plus 18x plus 12. All right, so then we need the critical numbers, which are where this is 0 or undefined. Okay, x, so I'm just dividing everything by 6 because it's the greatest common factor. Okay, and then this factors. Okay, so x is negative 2, x is negative 1. So those are the critical numbers. Okay, so then, all right, so they're the critical numbers. So I do a number line. Notice how I'm writing f prime on this number line because these values are inputs for f prime. Okay, so negative 2, negative 1. So since this is an f prime number line, I am plugging these like testing point values into f prime. And I would plug into the factored form of it. Okay, so up here, all right, so see how I factored like that? Yeah, you want to be plugging into like the factored form. Okay, so this is 6x plus 2x plus 1. And the reason why I want to plug like these values, like for example, negative 3 negative 1.50. The reason you want to plug these points into the factored form is so that you could just, instead of actually finding the function value, like the f prime function value, you just can think like in terms of positive or negative instead of like the exact numbers. So negative 3. All right, so this is going to be, so I plug in negative 3 here, and I get a positive times a negative times a negative, which is positive. Okay, and then negative 1.5, positive, positive, negative. So that'll give me a negative. And then I plug in 0, and everything is positive. Okay, so now, what are they asking? Local extrema. So, what we've got to do from here, all right, so now, so min, so I know I've got a min at negative 1 because f prime changes from negative to positive, and I know I've got a max at negative 2 because f prime changes from positive to negative. But I want to actually find the extrema. So finding the local min and finding the local max means plugging these values back into the original function. The extrema are on the original. Okay, min at negative 1. Okay, so local min is going to be f of negative 1. Local max is going to be f of negative 2. And then you've got to like plug them into a calculator. Right, and you're plugging into the original this time. Okay, so the answers, the extrema, are on the original function. So I'm plugging in negative 1. So that'll be negative 2, oh shoot, plus 9, minus 12, minus 4. I'm at school. Okay, equals negative 9. And then I plug in negative 2. And we get 2 times negative 8 plus 9 times 4 plus 12 times 2 minus 4. Okay. All right, I'll have to make another part to the video.